Welcome to BTFViewer. It is an AI-assisted tool for analyzing RTOS BTF traces. The basic rule is simple: find evidence first, then use AI to explain it. The desktop and web versions provide the same analysis features. In this demo, we use the web version and an 8-core sample trace. This trace is 2 seconds long. It contains data from 8 cores and 163 tasks. Several stress test phases were recorded in one trace, so some warnings are expected. We will first inspect the timeline and follow the diagnostic steps in statistics. We will verify each issue on the timeline before asking AI for help. From the File menu, select Open or drag a trace file into the window. BTFViewer supports both compressed and uncompressed BTF files. For this demo, we will open the included 8-core sample trace. The main area is the timeline. Each colored bar shows one execution slice of a task. Move the pointer over a bar to see its duration, core, and nearby slices. The status bar shows the full duration, active cores, and context switches. This trace is 2 seconds long. Its timestamps start near 1 seconds, not at 0. Most toolbar buttons use icons. Move the pointer over an icon to see its name. You can switch between horizontal and vertical layouts. Use Zoom In 1:1 or Fit to adjust the timeline. You can also switch between Task View and Core View. Load shows CPU utilization below the timeline. Heatmap and Chord show task migrations within the visible time range. To inspect the full trace, click Fit before opening these migration views. Analysis opens a short triage card of findings. Compare becomes available when at least 2 traces are open. Settings is at the far right. The right panel contains statistics, marks, find, legend, and AI. Start with statistics. Use AI only after the statistics and timeline show the same evidence. Load shows CPU utilization below the timeline. Core View groups activity by core. Task View shows one row for each task. Drag the divider to give the chart more space. Choose the view that fits your investigation, then use Load to compare CPU activity with the timeline. Start every analysis with 2 checks. Is the recorded time range useful? Are you viewing the full trace? Click Fit or use its shortcut to show the complete trace in the timeline. Open Statistics. The sections follow a diagnostic order: trace health, scope, load balance, CPU execution, latency, and concurrency. This trace contains 8 cores, about 31 execution slices, and measurements for priorities, mutexes, queues, and intervals. It also contains several test phases. Treat warnings as investigation clues, not confirmed defects. First, limit the analysis to one phase, then check each warning in order. Click Analysis on the toolbar. This dialog shows findings for the current statistics scope. Each finding has a severity level. Findings may cover load, long execution slices, blocking, migrations, tick health, or synchronization object bounces. When at least 2 cores are active, the dialog also shows the load balance score. Findings are not a separate statistics section. Each finding tells you which section to check next. Read every finding, not only the first one. Open the suggested section, then click a max value, chart point, or heatmap cell to move the timeline to the evidence. Confirm the evidence before asking AI to explain it. Step 1. Check whether the timing data is reliable. In statistics, open Trace Health. This trace uses tickless mode. The coefficient of variation is about 37%, which is much higher than the 5% reference for a stable periodic tick. The average period is about 945 microseconds. The largest gap is about 3 milliseconds, and the estimated number of missed ticks is 10. In tickless mode, the kernel skips ticks when no task is ready to run. Long gaps during idle time can therefore be normal. Limit the scope to a busy region and check trace health again before treating this warning as a defect. Step 4. Limit the analysis to the test phase that matters. A trace with several phases can hide an issue among setup, stress, and cleanup activity. Place 2 cursors around the priority inversion demo. Include the low, medium, and high tasks from about 3 to 3 seconds. Enable limit to C1 CN. Statistics and analysis will now use only this window. The status bar shows the time between the cursors. Open analysis again to create findings for this scope. We will clear the cursors for the full trace checks and restore this window for the latency check. Step 2. Check whether the cores share the work evenly. Open core utilization. The cores are about 57% to 75% busy. The load balance score is 95% and the spread or sigma is about 6%. Load imbalance is therefore not the main issue. Next, check core time breakdown, concurrent core active, and kernel switch overhead. Similar core utilization does not always mean low overhead. Frequent task migrations can keep the cores balanced while adding extra cost. Step 3. Find the tasks that use the most CPU and the longest execution slices. Open top tasks, then execution time per slice. Task CS27 uses about 15% of the CPU time. Several similar CS workers are close behind. CPU share is not the same as worst-case execution time. CS27's longest slice is only about 3 milliseconds. Sort execution time per slice by max. Idle tasks can look long because they run when a core has no work. Ignore them. Among user tasks, in C118 has the longest slice, about 110 milliseconds. Click that max value to move the timeline to the slice. Do not check only the average or the CPU share. A 110 millisecond slice is far longer than a 1 millisecond tick. You can set a deadline for each task under Settings, Display, Analysis Thresholds. The values use nanoseconds. Before deciding that the task itself is slow, also check preemption chain and mutex. Step 5. Check latency inside the priority inversion window. Blocking time measures how long a task stays off the CPU before it runs again. In this window, task high 268 waits up to about 53 milliseconds. Low and medium wait about 35 to 40 milliseconds. You can ignore runner because it sleeps between test phases by design. Blocking time is not the same as end-to-end response time. Dispatch measures the delay from task creation or resume to its first switch-in. Preemption chain shows which task preempted another task. Priority inheritance shows temporary priority changes caused by a mutex. Look for the red boost bar below low. Task PS228 shows the classic low, medium, and high priority inversion pattern. This pattern needs further design review. Clear the cursors to return to the full trace. Step 6 checks concurrency, migrations, heatmaps, locks, and priority inheritance. Task CS18 migrates about 1 times per second. Its average time on each core is about 0 milliseconds and its ping-pong count is high. This is migration thrashing, but it does not by itself prove lock contention. Common causes include task affinity or too many similar worker tasks. A lock bounce is different. It occurs when a task moves to another core while it still owns a lock. In task view, lock the highlight on CS18. With load enabled, the chart shows the task CPU share on each core. Heatmap and chord use the visible time range, so adjust the range first. Use lock bounces only when checking mutex movement. Next, open mutex and queue. One mutex has 864 holds and 9 cross-core bounces, so its status is warning. The queue has a stronger signal. 858 of 864 holds moved across cores while still held, although its status may still be okay. Check each warning on the timeline before deciding whether it is a real defect or only cleanup activity. Step 7. Check whether execution follows the firmware settings. Open core affinity. Mask lists the cores allowed for a task. Observed cores list the cores where the task actually ran. Violations lists any core outside the mask. In this trace, all affinity tasks stay within their masks, so violations is empty. Next, open task lifecycle. Tasks SR0 through SR3 each have 4 suspends and 4 resumes. Select SR0 and confirm that it does not run between a suspend and the matching resume. Runs counts scheduler dispatches, so it can be much higher than 4. This is normal. You can set deadline thresholds under Settings, Display, Analysis Thresholds. The values use nanoseconds. Find searches for tasks, migrations, software trace events, and intervals. Marks contains your cursors, bookmarks, and notes. Legend controls colors and filters. Right-click the timeline to add a cursor, bookmark, or note. When you reopen the file, the session restores the zoom range, cursors, and marks. Step 8. Save the results and verify the fix. HTML and CSV exports use the current cursor scope. The HTML report places analysis findings near the beginning. Trace Compare is on the toolbar after analysis. It becomes available when 2 traces are open in separate tabs. After changing the firmware, record a new trace. Use the same cursor scope in both traces and compare the same test phase. A what-if estimate does not validate a fix. The new trace must show the improvement. Step 9. Use AI only after statistics and the timeline show the same evidence. The assistant does not read the raw BTF event stream. It uses analysis findings, summary statistics, timeline queries, and comparison results for the current scope. If the scope is wrong, the answer may also be wrong. Open Settings, then AI, enable AI Assistant. This demo uses Google Gemini with the Gemini 3 flashlight model. Enter a Gemini API key, select test connection, and save the settings. You can also use a local Llama model without an API key. You can choose how much context to send. Compact reduces token use by sending only the highest ranked findings, relevant tools, and a short investigation history. Balanced is the default for most investigations. Full evidence sends complete findings, tools, and history for complex cases. Compact still keeps the cursor window, task names, jump times, key measurements, confidence, and the what-if disclaimer. If the evidence is insufficient, switch to full evidence and try again. Keep auto-apply GUI actions off for this demo. You can then choose apply or skip for each action that changes the view. Export actions still open a saved dialog. Results can change with the model, scope, or trace. The tool calls, wording, and timestamps may be different. Treat this video as an example, not a fixed script. The AI tab contains 6 stages: triage, scope, investigate, verify, experiment, and compare. An empty log shows start investigation. Language selects the reply language. Ask sends a question, stop cancels the current request, and clear removes the replies, resets the usage meter, and clears the current investigation issues. When the log is empty, select start investigation. This runs auto-investigate for the highest ranked analysis finding. For your first investigation, use the built-in prompt templates instead of a long free-form question. This example uses Gemini 3.1 flashlight. It took about 20 seconds, used about 128 tokens, and called 11 tools. Your result will be different. The selected finding is priority inversion on task PS228. It matches the low, medium, and high pattern that we checked earlier. The tool cards investigate the finding, detect priority inversion, query priority inheritance. Set cursors from 3055 to 3,055,153, zoom the view, and highlight PS228. The investigation also checks the critical path near 3,055,093, builds a task dependency graph, estimates a shorter critical section with what if, and adds a bookmark. If auto-apply is off, select apply for each action that should change the timeline. Read the reply in 3 parts. First, check the conclusion and its confidence. Second, follow the causal chain through each jump time link. Third, review the task dependencies and alternative explanations. In this example, the evidence includes a priority boost from 2 to 4, a migration from Core 7 to Core 6, and shared lock relationships with CS tasks. The evidence panel is created by BTFViewer, not by the model. It lists the current issue, tool reasons, evidence quality, cost, and conditions that could disprove the conclusion. Click every jumpy time link. Then check priority inheritance, mutex blocking, critical path, and the red boost bar on the timeline. Even if the model reports high confidence, verify the evidence yourself. Treat what if as an estimate only. This is the beginner workflow. Start from a named finding, follow the evidence to the timeline, and confirm or reject the explanation in statistics. A later run may select a different finding. Step 10. Verify the AI reply. Click every jumpy time link in the reply. The time value uses the trace time unit, which is microseconds in this file. The timeline moves to that point. Check the same event and metric in statistics. If the AI reply conflicts with the measured data, trust the statistics result and timeline evidence. The evidence panel lists the tools, the reason for each tool, evidence quality, and possible contradictions. Select a completed stage to jump to its output in the log. What if and optimize provide heuristic estimates. They are not scheduler simulations or measured results. To test a suggested change, update the firmware, record a new trace, and use compare. Do not choose a fix until the timeline supports the cause. Step 11. Explain one test phase instead of the full trace. Place 2 cursors around the priority inversion window from about 3 to 3 seconds. Enable limit to C1CN, then select explain region. BTFViewer includes the cursor bounds in the prompt, so every jumpy time link should stay inside this window. If a link points outside the cursors, it is outside the current scope. Do not use it as evidence. Confirm that limit to C1CN is enabled. Create new findings for this scope and ask AI again. After the investigation, you can create a diagnostic report from the AI tab. After a firmware change, record a new trace and use compare. The full beginner workflow is: find evidence, start an investigation, verify every jump time link, and use explain region within C1CN. This completes the BTFViewer diagnostic workflow. Open a trace and select fit. Check statistics, analysis, and trace health. If the trace contains several test phases, use cursors and limit to C1CN. Then check load balance, CPU execution, latency, concurrency, and configuration compliance. Confirm every issue on the timeline. After the evidence is clear, configure the AI model and select Start Investigation. Verify every jumpy time link and use Explain region within the cursor scope. AI can organize evidence and suggest explanations, but statistics and the timeline remain the source of truth. After changing the firmware, record a new trace and compare the same test phase. When the new trace confirms the improvement, export HTML or CSV to save the results. Thank you for watching. Open the 8-core sample trace in BTFViewer and try the complete workflow.